Hello everyone, welcome to CS70 Homework Review number 2. This time we're going to be looking specifically at problem number 3, Calculator Enigma. The problem says, suppose we have a calculator on which the only working keys are 369, the parentheses, plus, times, and minus, as well as the decimal point. We prove that the only numbers we can make are of the form 3k over 10 to the L for k in the integers and L in the natural numbers. In other words, the only numbers we can display are multiples of 3 with a decimal point inserted somewhere. Our hint is to use the well-ordering principle, which we will try to do right now. First, we must define what set we're doing well-ordering on. For this problem, let's consider all our expressions E. Here is an example of one such expression. 3.6 plus 9.3 minus 6.9 times 3.3. Initially, we might be tempted to order each expression by the number of buttons we might have to press to enter an expression into the calculator. Instead, why don't we order based on the number of operators, that is, plus, minus, and times, in the expression? For example, in an expression like we have here, there would be 3 operators. To draw another example, let's say we had 3.9 plus 6.3, or just 3.9. This expression would have 1 operator, and this expression would have 0 operators. So, if we were to label these expressions, let's say E1, E2, and E3, we would say that E3 is less than E2 is less than E1. Now, let's apply the well-ordering principle. We apply it on our new claim that expressions E with n operators can be expressed in the form 3k over 10 to the L, for k being an integer and L in the natural numbers. If we prove this new claim, we'll say Pn, for all n, then we have shown that this claim holds. When applying the well-ordering principle, it might be useful to draw out a number line. So why don't we draw a number line of all the natural numbers? We now consider 2 sets. R, the set of natural numbers where our claim above holds, and the other set, the set complement in the natural numbers minus R, naturally, no pun intended, the set of natural numbers where a claim does not hold. To picture this, we'll draw it like this, let's say. Notice that I drew that our set R would include 0, but we actually do have to prove this. We have to prove that 0 is an R. So why don't we do this right now? We claim that 0 is an R. So let's go ahead and prove this. So 0 is the set of expressions with 0 operators. So this would be something in the form 3.639, for example. So why would we know that an expression with 0 operators would be necessarily expressed in the form 3k over 10 to the L, where k is an integer and L is a natural number? First, let's try and generalize expressions of this form. We see that expressions like this can be written dn minus minus 1, dot, d2, d1, d0, dot, d negative 1, d negative 2, dot, 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 dm, let's say. What does this mean? Well, we know that these are each digits 3, 6, or 9. And we know that this, in decimal form, can be converted into a number we understand as the sum from I equals m to n. M is a negative number in this case, of di times 10 to the I. For example, a number like 93.6 would actually equal 9 times 10 to the 1 plus 3 times 10 to the 0 plus 6 times 10 to the negative 1. Observe that we could factor out a 10 to the negative 1, and we're left at 0 times 10 squared plus 3 times 10 plus 6 all times 10 to the negative 1, which is equal to 9 times 10 squared plus 3 times 10 plus 6 over 10 to the 1. We see that since 9, 3, and 6 are all multiples of 3, that this is in the form 3 times 3 times 10 squared plus 1 times 10 plus 2. Notice that this is exactly in the form 3k over 10 to the L. We observe that we can do that for any number in this form. We can always express it as 3k over 10 to the L by doing exactly what we did. That is, factoring out the lowest negative power that we might have, the lowest negative power, if there is one. If there isn't, then we don't need to, and we can just leave 10 to the 0, else we can say 10 to the 0. And then factoring out a 3 from the top, since 9, 3, and 6 are all multiples of 3. So we're left with exactly the form we want for an expression with 0 operators, where k will be an integer, and L is certainly a natural number. Therefore, we have proven our claim that 0 is in the set that we want, R, the set where P of n holds, so P of 0 holds. Note that you did not have to prove it this rigorously on the homework. Now let's move on to applying what we've just learned in the well-ordering principle. So, let's go ahead and redraw the number line from above of the natural numbers. And now we can confidently highlight that 0 is a member of R. Remember, we have the set R, where our claim holds. And the complement of this in the natural numbers, where a claim does not hold. Does not hold. To continue with the well-ordering principle argument, we now claim that the set where a claim does not hold is not equal to the empty set. In other words, our claim does not hold for all n. By the well-ordering principle, this tells us that there exists some least element, n naught in n minus r. So an element n naught, which is the least element. If n naught is the least element of R, this tells us that n naught minus 1, an even smaller element, cannot be in n minus r, since we claim that n naught is the least element, and therefore n naught minus 1 is in R. N naught minus 1 is in R. How are we certain that n naught minus 1 is a natural number? Well, we just proved that 0 is in R, and since n naught, the smallest element of n minus r, is definitely not equal to 0, we know that n naught is not equal to 0, then we are certain that n naught minus 1 is greater than or equal to 0, and so n naught minus 1 is certainly a natural number, which allows us to claim that n naught minus 1 is in the set R. To complete our argument using the well-ordering principle, we now make a claim similar to how we would in induction, that for all n, P of n implies P of n plus 1. This tells us that if n is in R, then certainly n plus 1 is in R. So just like in induction, we're going to assume that P of n holds. In other words, our claim holds for an expression with n operators, and we will now look at an expression E with n plus 1 operators. So, we observe that our expression will look something like 3.6 minus 6.99 plus 6.9 times 9.6 plus 3.3. Let's say it looks something like that. So let's say that this expression has n plus 1 operators. We observe that we can separate this expression into two sub-expressions. This expression here with n operators, and this sub-expression here with zero operators, Generally, we can express an expression with n plus 1 operators as E1 with some operator E2, where E1 has n operators and E2 has no operators. Remember now that we assumed P of n and we proved P of 0. So now we can apply this and say that our expression E, which can be expressed as a sub-expression E1, an operator, and another expression E2, can be expressed in the form 3, say k1 over 10 to the L, some operator, 3, say k2 over 10 to the L2. So this is L1, where k1 and k2 are integers, and L1 and L2 are natural numbers. Now we proceed on a case-by-case basis based on our choice of operators, starting with, let's say, plus. In this case, we have 3k1 over 10 L1 to the L1 plus 3k2 over 10 to the L2. With some algebraic manipulation, we see that this is 3k1, 10L2 over 10L1, 10L2 plus 3k2, 10L1 over 10L1, 10L2, which is equal to 3k1, 10L2 plus 3k2, 10L1 all over 10L1, 10L2. We see that this is equal to 3k1, 10L2 plus k2, 10 to the L1 over 10 to the L1 plus L2, which is of the form 3k over 10 to the L1 for k in set of integers, L in the natural numbers. We proceed by proving our claim for the case where we have a minus, in which case we have 3k1 over 10L1 minus 3k2 over 10L2. Using the same algebraic manipulation from above, we have 3 k1 10L2, but instead we have minus k2 10L1 over 10L1 plus L2, which again leaves us with the form 3k over 10 to the L, for k being an integer and L being a natural number. So now all that's left to prove is the case where we have a times. So we have 3k1 over 10L1 times 3k2 over 10L2. We find that this is equal to 3k1, 3k2 over 10L1, 10L2. Seems like we just wrote it side by side. But we find that this is equal to 3k1, 3k2 over 10L1 plus L2, which is again in the form 3k over 10 to the L for the above. So in all three cases, the exhaustive cases where it's a plus, minus, and times, we have proven that our expression E with n plus 1 operators can be expressed in the form 3k over 10 to the L for, again, k being an integer and L being a natural number, assuming that our claim can hold for n operators. Therefore, we've shown that for all n, p of n implies p of n plus 1. We argued that this tells us that if n is in R, then n plus 1 is certainly in R, since if a claim holds for n, it will certainly hold for n plus 1. Therefore, we can say that because our claim holds for p of n naught minus 1, then certainly our claim holds for p of n naught. However, this is a contradiction because we claimed that n naught was in n minus R. In other words, that our claim did not hold for n naught. Therefore, our original assumption that n minus R was not the empty set, which allowed us to say that n minus R had a least element, is false. We have a contradiction. Therefore, n minus R is the empty set, and therefore R is equal to all natural numbers. So our claim Pn holds for all natural numbers, and so for any number of operators, and therefore our original claim that everything in this calculator can be expressed as 3k over 10 to the L, for k being an integer and L being a natural number. Therefore, this claim holds. And so, we are done with this proof. See you in the next video.